All right, scholars, we are going to push forward in talking about projectile motion. Projectile motion is things that are falling due to gravity. So far, we've looked exclusively at problems where things are launched horizontally. So as an example, number 27, which we have completed already, so this ball is thrown horizontally. What we want to be able to do is generalize this. So for example, we'll work our way up to a question like this. Basically, a daredevil like Evel Knievel is going to jump over some buses using a ramp and having some initial speed. Can they clear the buses? We will find out. But before we do that, we're going to start with a stripped back, a more simple example, number 26 here. So this involves someone kicking a ball, and they give us just two pieces of information, and we can figure out everything else from that. So we'll read the question. We will write it out. I'm going to talk about how to solve this in general, and then we'll actually work through to solve number 26 here. So this says a ball is kicked with an initial velocity of 16 meters per second in the horizontal direction and 12 meters per second in the vertical direction. At what speed does the ball hit the ground? For how long does the ball remain in the air? And what maximum height is attained by the ball? So we'll take those one at a time. Let's start where we always start, by drawing a picture. So I'm going to very crudely draw a person kicking a ball. Of course, it doesn't really matter how good our drawing is. What we're told, though, and as you read more of these, you'll get better at understanding this, but we're told that it's kicked up at some angle. They tell us that by giving us the horizontal and vertical speeds. So let's do it like this. Let's break it out. We're going to turn this into some vectors here. So we've got a vertical and a horizontal component. What we would say is that this hypotenuse is v naught, okay, the initial velocity. And then, of course, right now we don't know the angle, but we could figure it out if we really wanted to. Instead, what we're going to do is just simply label this with the information given to us. So it says 12 meters per second in the vertical direction. So we would call that v naught, since it's vertical in the y, that's 12 meters per second. And v naught x is 16 meters per second. Okay? So you can see we've got a triangle going on here. Your brain should be going to things like Pythagoras. Your brain should be going to things like sine, cosine, and tangent, etc. Speaking of that, even though this problem doesn't require it, what I want to do is just give you a preview of where we're going with this. So even though we don't need it, what we're going to do is we're going to set up the trig relationships with this triangle here. So in an effort to blend this problem with a little bit of notes, I want to talk about how we would set this up if we didn't already know these components. So I think it's really helpful anytime that we're solving with triangles not to try to carry the information around in our brain. Instead, let's write it on the paper. So I like to start with sine. I know sine theta is, so it's SOHCAHTOA, opposite over hypotenuse. So sine theta is opposite over hypotenuse. Cos theta is COA. So it's adjacent over hypotenuse. And tan theta is TOA, T-O, so opposite over adjacent. Now, what we mean is opposite is the one across from the angle. So if our angle's down in this corner, this length here is the opposite. The hypotenuse is always the longest, and then the adjacent is whatever one is left over after that. So what we want to do is we want to set up our trigonometric relationships. That's fun to say. And I'll do this in red so that you can see I'm actually filling it in. So we don't want to guess here. We always just want to be careful, write everything out, and let's see if we can figure out what these are. Actually, take a moment on your paper, see if you can write what are the relationships using these variables for sine theta, cosine theta, and tan theta. All right, for sine theta, you should have gotten the opposite over the hypotenuse. That's v naught y over v naught, and if you were paying careful attention, that means we have sine theta equals 12 meters per second divided by question mark. We don't actually know this. Okay, now of course we could figure it out if we wanted to using Pythagoras. We won't at this moment, but we may a little bit later on. Let's do cosine. So cosine was, of course, adjacent. That's 16 meters per second, or v naught x over v naught, and that's cos theta is v naught x is 16 over, again, we don't know, question mark. Okay. Finally, we have tan theta, that is opposite over adjacent, so we just have v naught x over, v naught y, that's our opposite, over v naught x, that's, tan theta is 16 over 12 meters per second. So that actually comes out to a number. Tan theta here is, divide both by 4/4. Okay. Now, we could work backwards and find the angle. We won't do that just right now. Okay, so that ends our bonus set of information. We're going to work now toward figuring out some of the things in the question. So moving on, we have our picture. We should always then write down our equations. So we're going to write down our projectile equations, which we learned last time. So in the x direction, we have just our one humble equation. And in the y direction, we have our three equations. Remember the assumptions we're making? We're assuming no air resistance. We're assuming that g is constant. We're assuming we're near the surface of the Earth. So I'm going to pause so I can just jot them all. There we have our four equations. And now what we want to do, that we've got all of them written down, we want to see if we can answer the question here. So the first one asks, at what speed does the ball hit the ground? That's right over here, A. So we want to know, what is V final? Now, let's go back to our diagram and see if we can show where that would be. So, we've got our components here in the x and in the y. And, okay, this is V naught. We want to know, well, what speed is this going to hit the ground at? Okay? And because of symmetry and the fact that we've kicked this here and it lands at the same height, then it's going to be hitting the ground at the same time. And what we're essentially going to have is this triangle, but rotated over to here. Okay? In other words, the x velocity doesn't change, and the y velocity should be identical as well. So we'll label those on here. V naught y, that should be equal to V final in the y. We have over here V naught x, that should be equal to V final in the x. Okay? So by symmetry, we actually have showed here that the ball is launched and it's actually going to land at the same speed. Now notice they don't ask for velocity. Here we just want to know the magnitude. We just want to know the magnitude of the final velocity. So it's going to be this same triangle, but instead of being pointed upward, it's going to be pointed downward. Forgive my poor angle drawing there. But that just means that the x velocity is going to be the same thing. So V final in the x is going to just be 16 meters per second. And you can see again through symmetry that our, sorry, I was covering that up. You can see by symmetry that this y velocity at the end when it hits the ground is going to be the same as the initial, but just going downwards. So we can argue by symmetry that V final in the y is just negative 12 meters per second. And we're after this thing here, the hypotenuse. So we can use our old friend, the Pythagorean theorem. So VF squared is going to be this squared plus this squared. We got to be careful to use our, we got to be careful to use our parentheses and square everything. I'm going to pause and see if you can give me the correct answer. All right, so I have installed into the Pythagorean theorem a squared equals b squared plus c squared. I've installed in my numbers, I square them, I keep my units together, I get 400 meters squared per second squared under the square root, which comes out to 20 meters per second. That is our answer. Now again, this is the same speed that it was launched at, so actually we get for free that this is, so we can just say V, oops, we'll put it down here. We'll say V naught, oops, is also 20 meters per second. Okay, but this is what they wanted for A. Excellent. Let's move on to part B. All right, the next question says, for how long does the ball remain in the air? So there's several ways that we, of course, can answer this. Let's think about this. Oftentimes when we solve a problem like B there, we want to try to make something 0, so that's going to make our life easier. Let's take a look here. We need time in the equation. We want to know some of the information in there. So let's look at these one at a time. Okay, well, let's look at this first one. Do I know the displacement? I actually do. I don't know if we labeled it on here yet, but let's take a look. So it's kicked here. It moves some horizontal distance. I'm running out of space here, but let's call that delta x, right? It moves that distance. It goes up in the air, it goes down, but when it gets over here, well, actually, it hasn't gone anywhere in terms of the vertical direction. So I'm going to label this, the y displacement is 0. So this is kind of great. For this one, delta y equals v naught yt minus 1/2 gt squared. Hey, this is great. Our y displacement is 0. Let's look at what else we have. Maybe this is the right equation. Okay, we have v naught y. Yep, we know that. That's 12. Okay, we don't know t. That's a problem, but that's actually... Oh, no, that's good. That's what we're looking for. For how long does the ball remain in the air? Yep, we're looking for t. Hey, and we know g. Hold on. We know how to solve this. So let's do this. Okay, let's add 1/2 gt squared to both sides. Since this is 0, since that's 0 and it's gone. And let's see what happens. So this side's going to be 1/2 gt squared, and that's going to equal v naught t. Okay, that looks odd. We have a t squared on one side. Wait a minute, I can get rid of a t on both sides. So divide both sides by t. So that's going to cancel a t on both sides. Okay, moving forward, I have 1/2 gt equals v naught y. Hey, this is good. This is good. So we can solve for t now. Okay? We know g and okay, this is great. Also keep in mind we've accounted for the negative, so when we plug in, we're going to go 9.8. See if you can calculate the time it spends in the air. Okay, so I did some algebra working out. You can pause if you need to see how I did that. I get to this equation here, which would be what we might call the hang time. In other words, when the y displacement was 0, we launched here and landed over here. The y displacement is 0. This is the amount of time it spent in the air. This is actually going to be true if we're ignoring air resistance for any projectile that launches and lands at the same height. We plug this information in, and we get 12 times 2 divided by 9.8. It spends, according to my calculator, 2.4, we're going to round that to 5 seconds in the air. Okay, very nice. All right, so what we're going to do now is try to address question C, and I'm going to try to do my best to cram it right into the middle there. We're going to do this in blue so that you can see the difference. Okay, so C says, at what maximum height is attained by the ball? Okay, this is a little tricky. We know that when we throw something up in the air, that it reaches its maximum height and it stops moving upward and starts moving downward. You can see that right here. At the top of this motion, the ball is certainly still moving sideways, so its Vx equals V naught x. In other words, it hasn't slowed down in the x direction, but of course at the top our Vy is 0 meters per second. So that's really useful. What we can do is we can use some of the information we already have and find out what maximum height that's going to be. So we can exploit this fact, or we could do this, okay? We know that the time that it spends in the air to go all the way from here to here is this number, 2.45. So if we wanted half of the hang time, we would just divide that by 2. I'm going to go with that option, okay? I'm going to go with that option. So we'll say T full, the full time, the full hang time, is 2.45, and T, let's say T half, is that but divided by, that's seconds, that but divided by 2. Awesome. So that looks like time in the y direction. It's not, it's half time. Okay? So let's calculate that real fast. So I got the half time. I'm going to keep all my digits just for right now is 1.2 225 seconds. And what we can do now is we can actually use, well, there's a couple equations we could use, but I think this one's going to be our best bet. So check this out. We're trying to find the maximum height. So I know my diagram's a little bit messy, but we're trying to find what is delta y at the highest point. We want to know what that information is. So we need this. We know this. The initial velocity in the y direction is 12. It was given to us right away. And now we need to find, enter just the times and the acceleration due to gravity. So actually, because we did all this hard work to get this time, this is a pretty straightforward application here. So let's do this. The maximum height at the half time is going to be v naught y times t minus 1/2 gt squared. Let's see if we can squeeze all that in here. So the maximum height is going to be 12 meters per second. Actually, you see if you can get the right answer here. All right, so I kind of ran out of room on my paper, but we got delta y, the maximum height is 7.35 meters. I simply plugged everything in. This is the maximum height. That is our answer for C. Excellent work, folks. The only thing that's going to get more challenging about this is that in the very near future, instead of straight up giving us these component velocities, they'll instead give us the initial velocity, which is easier to measure, and the angle, which is pretty easy to measure. But otherwise, all the problems look just like this. It's just applying what we've learned about physics. For example, that the y velocity hits 0 at the top. For example, this is a 0 y displacement. And then we're just applying that to these various equations. Sometimes we'll pull in our old friend Pythagoras or these trig identities. Thank you so much, scholars. Have a wonderful rest of your day.